Okay, welcome back, everybody. So I'm very excited to talk about today's lecture. So today we're going to finish the chapter 2 of your book. We're going to finish talking about the form factor of particles, review that one more time, and we're going to talk about form factor of a polymer chain. And after that, we're going to go to a little bit into the structure factor, starting with a little bit more complex disorder system, okay? Then next lecture, we're going to go into more detail. So let me begin by address the question from the last class. We asked about what is form factor and structure factor. And by now, you should know it, right? So form factor deals with individual structures, scattering. So examples are scattering from a single nanoparticle, single polymer chain. Structure factors deals with how these particles arrange with respect to each other, or how the polymer chain packs with each other. Or later on, you will learn how these crystal lattices are packing, such as phase center to cubic, etc. So you can get all the lattice parameter needed. So what's the difference between them? I think just to explain. Significance of inverse space. So why we started inverse space at all? That comes down to the answer that because the scattering deals with the Fourier space. So everything X-ray is probing is in the inverse space. I'll talk more on this topic today. So inverse space is basically essence of how X-ray sees the world. It's a slightly different than our eye sees, but that's the reason, okay? So today's question, I'll tell everybody before the end of this lecture. I see some of you still, right? So today's lecture, let's revisit a bit of what we talked about. So I want to start from this slide. So why at all we're learning this part of very challenging theory is where I want to visit again. That comes down to fundamentally how you should look at the scattering. Scattering originates from the interaction of your X-ray with the electron. X-ray just to see the electron clouds. It doesn't see nuclear, it doesn't see the vacuum or anything in between. It doesn't act as like a physical ball or particle hit your object, then bounce off. Okay, it doesn't interact as light. So electrons is basically the units. So we talked about what the form factor of atom, which we can assume there's even electron clouds from the center to outside. So it's basically a spherical shape. To a little bit more complex is to such as nanoparticles, which has also assuming uniform electron density at low Q scattering angle. Okay, then you also have some more complicated, such as molecular, we're going to talk about today, which ties in very well everybody's polymer physics class and lecture. Okay, so this is where Fourier transform were introduced. If everybody recall how we can understand electron density and expressed using the scattering vector and Fourier transform. So it basically says Fourier transform of your electron density within your particle or within your structure could give you the form factor. So if I know the shape and I know the average density or where the electron reside in me, you can do form factor of Dr. Gu. But that's not so interesting, right? We are more interested in molecular. So Fourier transform, a quick review. Basically, this transform, a constant, for example, in the real space is on the left. Your inverse space is on the right. So a constant intensity, electron density, from the center of your object, in this case, it's a constant line, would transform into intensity high in the center, then decays. So this goes down to sine theta divided by theta, or sine x divided by x function. And that we also know So we're going to begin by go a little bit deeper about spherical particle. So how do we deal with spherical particle in terms of their form factor? Same. This is a universal equation, but it needs to be under the circumstance that our solution is very dilute. So let's review it slowly. Integrate over all the volume, electron density of your material. This is the integration of the scattering vector Q multiplied by the distance vector within your given material. So R, right? We talked about that. So for spherical particle that we know, integration of the volume can be further simplified by looking at the distance from the center of the radius to outside. So we just need to integrate the radius from 0 to how long your structure is, right? Or what the radius are. So 4 pi r squared, what is this first term? That's the surface area of a given sphere, right? 4 pi r squared is the surface area. So we consider how each, when we go in from the center, if we cut like a peel and onion from onion, so from the outside, the given distance is going to give you a little bit bigger volume. So 4 pi r squared low density ID is basically a form factor describes what a spherical object is. Ben, please.
I'm sorry, I was just
Okay, that's why you have a question. Based on what we know, the integration of this portion can be rewrite as just simple sine QR divided by QR. So we talk about this is a Fourier transform of this scattering vector. Not too difficult. So all we need to do is address how to do a mass form of 4 pi r squared, density rho r, sine q. Q is scattering vector, r is just any distance within your particle. Then you can integrate out this particular form factor for a spherical object with uniform electron density. So this generally applies to polymer particles, gold nanoparticles, any particle that adopt a spherical structure when we do scattering at the small angle region. Okay? This, again, gives you a simplified equation of what we have shown here. Now we can simplify. We need to integrate sine QR divided by dQr. This part is already, just look at the right part, sine theta d theta, right? This integration is already known, which I wrote in there, okay? If we replace that integration function with sine x minus x cosine x, we can get our form factor for a spherical particle, which is given by this quite simple equation. Okay, so 4 pi rho with a dashed line on the top means average density. Average electron density is just how much electron density within the particular volume. Okay, and we just replace x with qa. So this gives you the generalized form factor for a given sphere. Okay. So we can do a couple things to further simplify this, to convert this into this particular equation. And I'll explain why we may want to consider this approach. Phi x, generalized, phi is just a function. So phi x will be equal to 3 sine x minus x cosine x divided by x cubic. Okay? So this gives you a very easy way now to visualize form factor for any particle. It's basically, we can pull out this particular term in the front. If you look at, this is basically volume multiplied by density. So this gives you total number of electron n. Significance, if we plot this function, a little bit complicated, but if you assume this is a y equal to 3 sine x minus x cosine x divided by x3, that's going to be the form factor of your spherical structure. Okay, any spherical structure will adopt this scattering exactly like that. So this is basically the phi x function. Form factor for a sphere, which is shown here. It starts from the top, and it's actually crossed the 0. There's a part of that, the interference of the electron will give you a different pattern, which is give you negative phi x. And that just means there's a negative phase. And don't worry about phase, because X-ray detector measures intensity. And intensity is just the amplitude square, okay? So if we take a square of all the y, while maintaining all the x the same, we would come into this particular equation or plot. F squared is basically any data on the left, we take a square. So if you throw a spherical structure in your X-ray instrument, you plot intensity versus Q, that would mirror this exactly curve.
I have a question.
Yeah, Ben.
So is the scattering intensity always the form factor squared? Is that like a true statement when you say that?
Yeah.
Okay, always.
So for intensity is always related to the amplitude of your wave square. And amplitude of your wave is defined by form factor, okay? So you always measure form factor square, what detectors see. Lena, please.
I just was wondering, then why wouldn't it just be phi squared? How come it's f squared?
Okay, good question. So f is a form factor. Phi is just a simplified function. So your form factor is defined by electron density multiplied by phi qa. Okay, so that's a form factor. And the reason we write, this is a constant, so we don't need to plot it. It doesn't matter that much. We just need to plot the phi x. That's a form factor for spherical structure. So a very interesting part is the first dip. This 0 is translated to this 0. I think this textbook artificially showed a gap. There should not be much gap. Unless this is not plot exact to 0. There are some backgrounds, then that's reasonable. You have a little bit gap. So the first minima in your measured intensity has a significant physical meaning. The physical meaning of that is we can use that to understand what the x value when it's hit the 0. Okay? Right? So there's certain physical meanings for x. When y equals to 0, there is a certain value for x. That's when x equals to 4.493. In the spherical structure, you would have a y value equals to 0. And you have more higher orders. But the first minima has most useful, because it generally is most well defined when you measure a spherical particle. So you look at here, you measure first the value of x, which in our scattering measurement is the scattering vector q. You use the value 4.49 divided by q, you can get the diameter of your particle. Or more accurately, this is actually the radius, not diameter. So it's half of the diameter, okay? We will show a couple examples in the next slide. But that's a practice we did for understanding how the spherical structure will give out scattering. If you recall the schematic I give you, we basically performed a Fourier transform of average electron density within a spherical structure. That gives you the form factor equation, and this particular curve shows you what the form factor for what a spherical structure is. And what would be the intensity equals to? N is just number of electrons. This will not change the shape, but it will change the height of it. So most electron-dense material, gold nanoparticle, compared to polymer nanoparticle, we're going to scatter more because there's more electrons in the given volume. So your intensity will be higher. You tend to get better statistics or better, you can lower your measurement time without sacrificing the data quality, okay? Uh-huh. Yeah, please.
Just to clarify, the first minima is the radii. It tells you the radii of your spherical particle?
Yes, we're in first interceptor. We will cover a little bit more. I think I have a couple more slides. But by measuring this is not what we are measuring. This is a form factor we calculate. Detector sees intensity versus Q, which is exactly this curve. So if you know with the value here, you can calculate your radii. So in the textbook, it gives example. Let me jump into that. I'll show you a real example. So this is a SAX, small angle X-ray scattering data for a dilute suspension. We know why it needs to be dilute because we want to look at form factor. So that's about 0.1% volume of polystyrene sphere. This sphere, I believe it is 100 nanometer in radius R. So what we're plotting is log intensity versus the Q scattering vector. And you will see almost the same shape, but it slightly have a different decay value. We're going to talk about why there's a decay in high Q just a second. But you can observe what this local minima and mark where the Q value is and use very simple equations to calculate what is the radius of your particle, okay? That you can do. So now let's take a look at the real scattering data. This is simulated, but it's very close to what the real, okay? So you can think about this is example show here is a 100 nanometer radius particle. So what's the difference between this? No difference. Should be exactly the same. Your factor, maybe in here, your background will mess up some of the fringes, so it's not going to go as low, just because there's scattering and detection noise. So it might not go to 0, okay? But this is the first dip. You can use exactly 4.49, divide by that to get the radius of your particle, okay, using this particular equation. Make sure it's the first, because if you use second, then your value will be off. Then this modulation comes from the form factor that at higher value, your intensity can decay with the scattering vector Q. Okay, that's very common. The higher the Q, the weaker the signal. So, which is reflected by here. If you look at this equation, when X goes up, because X cubic is at the bottom of your equation, so when X is closer to infinity large, this top will be very small compared to the X cubic. So it will always, scattering will always diminishing in intensity at high Q. So which is why intensity in the low Q, if you look at normalized intensity, this is 1. This is almost 10 to the minus 5. So that's little signal. Okay? So looking at this generalized scattering, there's two very useful concepts everybody should learn and understand. There's two regions. We call it Ganier region and the Polaroid region. Not the Polaroid camera everybody may heard about, but this is a Polaroid, P-O-R-O-D. So what's the difference between this Ganier and the Polaroid? These are just the two famous X-ray scattering pioneers. They discovered some region of X-ray can be specialized for a certain application. I'll explain more detail. So Ganier region, specifically refers to the plateau of scattering at the low Q. Low Q, Q is scattering vector, so any data that is on the left of the graph is relevant to Ganier region. So what's the significance from this part of the data? It's quite abstract, right? So I have a great idea to help everybody to understand and visualize it. So again, think about this classroom. So what's the scattering vector Q we are plotting? Q equals nanometer inverse. So I need a volunteer to tell me again what the Q value and what's the significance of scattering vector. Come on. You guys did a good job in the Q.
It's like your structural information in inverse space.
Yeah, inverse space. That's what I want to hear. So Q is inverse to the size Q. You can use 2 pi divided by Q to kind of visualize a ruler, what we are looking at. Or if you want simple, just to use 1 inverse of Q. For a quick reference of the size Q we are looking at. So this is roughly, if you use 1 divided by this value, this is roughly about 100 nanometer. And if you multiply by 2 pi, this roughly translates to a real space of 600 nanometer. Okay? So if I could plot a scale in the D, in the real space, this would be 600 nanometers. So somebody tell me how big is this? Please. What would it be Q equals to 0.1 nanometer inverse translate to real space?
About 60.
About 60? Great. Great, Isaiah. I like it. So how about this one? Q equals to 0.3. What's the real scale it translates to?
20.
About 20. So, however, the X-ray measurement can go very high Q. It can go as high as, let's say, 2 nanometer, 20 nanometer inverse. So what would be the size scale we are looking at if it's 20 nanometer inverse? So even higher. So keep going, 20 nanometer inverse will be somewhere here. But what's the real space? Roughly 3 angstrom. Okay? Roughly 3 angstrom. So that's what I showed everybody at the beginning of the lecture. X-ray can see any features between a few angstroms all the way to a few hundred nanometer. So now you think about how to read this graph is to get a ruler, and the ruler goes from, okay, I got a 600 nanometer ruler. So what is the feature I can see at this length scale in my material system? And if keep going smaller, what size scale we can see? Let me go through one slide quicker because I like this slide. Just look at it here. SQ is structure factor, but it's basically, you can read it as intensity versus Q. So what is, this basically shows in scattering at different length scale. So this draws a polymer dissolved in solution. And apply what I showed you. If we assume this polymer has a size scale about, let's say, radius of gyration about 30, 40 nanometer. Now, when we do a scattering, we actually sample all kind of size from 600 nanometer all the way to a few angstrom. So it's like I having a measurement tape. I pull a nanometer, I measure this desk. I pull a feet, I measure this desk. I pull 10 feet, I measure this desk. What do I see within? So if I apply the same concept to the polymer solution, in the low Q region, we are really looking at a size scale much bigger than our polymer coil, right? So remember, what is 2 pi divided by Q? That's about 600 nanometer. Our individual coil is only on the order of 20, 30. I have a ruler about 20 times bigger than this, so I can measure exactly the shape, diameter, etc. of the particle. Okay? Conceptually. So now if I start to go into the higher Q, what happens in my ruler?
Measuring smaller things.
Where my ruler is getting shrink and shrink. So I could only look at up to the size scale of my ruler size. So when when my ruler, or which shows the size scale we are looking at, we look at now individual chain. And even higher Q, we only can look at part of the individual chain. So what happens within your molecular? Okay? So even higher Q, we are looking at segments of molecular or inter-domain packing in the crystal ladders, etc. So that's the significance of the Q at different length scale. We are looking at different features. There's a couple significance. So how do we understand intensity versus the Q? So this basically says when a ruler goes up, how much more things or scatters within their size scale. So let's take a look here. In the Guinea region, if my size scale is much bigger than my particle, then I only see the structure and overall shape of my particle. So this is the significance of Guinea region. Let's go back again. So Guinea region is when you see the intensity is a plateaued. It's signal of your measuring the whole overall shape of your individual dilute material. It can be a particle, it can be a plate, or it can be a rod. So this happens at very low Q. And you need to make sure your 2 pi divided by Q is larger than expected size scale of your structure to observe the Guinea region. So if your instrument can only measure to here, let's say here, you will never be able to see the appearance of this region. Okay? And it's generally harder to measure larger features because the bigger the feature, the region going to shift to even lower Q. That challenges how we can measure it using our instrument at here or at the synchrotron. Yeah, Ben.
For instrumentation, we usually refer to it as SAX or VAX.
Yeah.
What's the defined point between SAX and VAX, or is it kind of like both?
Yeah, very good question. So I think that's a common question we have. Let me show you one thing. I think I might have something for you. So this is actually the one slides prepared by Luke. I was planning to talk it in the future, but we can chat about that. So this is instrumentation. Everybody see that, right? So how do we measure the Q? It's a little bit deviation, but I want to cover it using 4 or 5 minutes, okay? How do we measure the Q, the scattering vector? We know the intensity is basically, detector sees how strong your intensity are. The more X-ray photons it collects, it shows a more stronger intensity. How about Q? How do we collect Q? What is Q equals to? What is scattering vector Q equals to? Oh, come on. If you got this one right, I'll get you a donut. Scattering angle. Yes! Both of you are right. So scattering angle, or 4 pi sine theta divided by lambda. So 4 pi and lambda is defined, but you only need to measure the angle. So how do we measure the angle using this instrument? It's coming from this paragraph. So it's a simple triangle relation. If we know where the sample to detector distance are, and if we know how far our scattering is away from the center, let's say L, and let's call it STD, or probably R is easy for everybody to understand. Radius from the center. So you can calculate this theta to be tan in theta equals to R divided by L STD, right? So you just need to measure in the measurement, understand how far you load the sample away from your detector, and how far your material bend the X-ray from the director beam. This is basically can be translated into distance. So you can measure the angle. Not hard at all. Sounds complex, but the instrumentation has considered everything. If you measure the sample, the software will give you intensity versus Q plot. So answer Ben's question a bit further. So the theta is generally small angle is field, then smaller than a field degree. Commonly, theta will be less than, I would put a number 2 to 3 degrees. In X-ray scattering, because we measure Q, and Q also translates to scattering angle. The lowest of the scattering angle is defined by the beam stop, because we always need to block the direct beam because it's so intense, it's going to either destroy your detector or overpower your signal. So we always put a piece of metal to block it. So the smallest angle we can bend is defined by this tiny beam stop and what the Q range we can get there. The largest is a Q by a certain range is defined by how close we can move the detector and how wide our detectors are. So in our setup, we can go up to about, I think it can go up to 40, 50 degree angle. And this translates to really small Q. So in the next slides, this gives you an idea what the Q range we can measure at different sample detector distance. So this translates to STD, how far you move your detector to your sample. And if we move the detector a little bit further away, what happens is we can probe lower Q region or larger features, but we sacrifice the other angle. So small angle typically is somewhere STD going to be 1.2 meter and above. So wide angle is typically very close using this geometry, 0.23. If I have to translate angle, I think this is probably on the order of 45. This probably is 20. This is probably a few degree. Okay, you can do a conversion in the theta angle from the Q. But did I explain it to you? Okay. So our tools has a lower limit about looking at Q up to 0.02 or 3. Okay, that's about this range. When we move the STD to about 3.8 meter, which is the longest distance we have. In our lab, we can move to 6.4 meter, but we rarely use that just because our beam is not that pure and diverge a bit. All right, so let's go back to the Ganier plot. That's important. So why we need to investigate in this low Q region? Large feature, low Q. Keywords for the Ganier. If you don't understand anything else, just remember this is in the low Q. It looks like overall shape of your structure. Physical meaning is when the scatter vector is larger than the particle, it can measure the particle size in a layman's term. Okay? So how does it work? Very simple. So same scattering function for the spherical structure, but if you when the X is very small, in the small angle region, okay? This generally applies to Q is Q going to be multiplied by RG going to be equal to 1 to find the onset. So Ganier region is really RG need to be larger than 1 divided by Q. So you can simplify by this Taylor expansion. We don't need to go into too much detail, but if you did Taylor expansion for sine x, cosine x applied to there, your scattering form factor for the spherical can be simply written as this, or more commonly, phi squared is what we measure in terms of intensity. Going to be relevant to 1 minus x squared divided by phi. Okay, keep an eye on this. Then if we reapply the relationship between intensity versus form factor square, this is just a number of volume average intensity. This is a constant. Don't need to worry about too much. If we replace the Rg to this QA square, we can arrive at this final Ganier region equation. Intensity going to be proportional to n is number of intensity per volume. So that's relevant to the concentration, scattering length density per particle. It's basically tell you how many electrons totally you have in that system. It's defined if your material is PIC. It doesn't change with anything else. This is the important part. It's equals to intensity equals to 1 minus 1/3 QRG squared. Q is scattering vector. Rg is radius gyration. In your nanoparticle, Rg has a value about like a 3 divided by 5 root square multiplied by radius. Okay, it's slightly smaller. If you still remember my polymer physics class, that's not too hard, right? So I will come back to this polar region, which is generally high Q. We're looking at the tiny features within your structure. As I explained, 2 pi divided by Q is going to be smaller and smaller. We are looking at tiny features. So if you look at this classroom, it's going to be part of my arm or part of my body instead of like whole shape of Dr. Gu. So significance is, in the low Q, we know how the intensity scale with Q and Rg. We can actually use this as a second way to measure Rg. So you can apply very simple plot log intensity versus Q square. Log intensity versus Q square. Log intensity, Q square. Same data, okay? But we can only use the Ganier region. So any data from this region, we replot it, put the log scale in Y, X scale square. That's the same dip as this first dip. You can now fit a linear fit in the region. It's going to deviate always at the higher Q, just because the Taylor expansion is no longer valid. But look at here. You can measure the slope going to be equals to 1 minus Rg squared third. You measure the slope, you get the Rg. Okay? So that's how people use the Ganier region. The trick is you want to make sure your sample is dilute. You want to make sure you measure low enough Q to reach that region. Okay? How low the Q need to be? It needs to be smaller than 1 divided by Rg. So if your Rg is expected to be 100 nanometer, your Q at least needs to be smaller than 1 divided by 100 nanometer, which is 0.01 nanometer inverse. Okay, if you don't reach that, you plot this, you come back, say, Dr. Gu, it doesn't work. I tell you, you haven't reached Ganier region. Ganier region doesn't apply to this part. Okay, you have to reach this part. Any question for Ganier region? Ben?
So Ganier region is dilute solution, but after that, does it matter how dilute it is since we're not measuring particle size? Or does all experiments, does it need to be dilute?
It needs to be dilute such that the particles are far away. So it don't need to be super dilute. Once your interparticle spacing is much larger than your Q, so in this case, your Q is looking at somewhere about 600 nanometer. So you know if the particle distance is bigger than that, then that's not a problem. Particle distance, let's say 1 micron versus 2 micron versus 5 micron, none of them will interfere with much of the scattering data. But don't over dilute it, because you're going to have a problem, have the sample to be super, super weak in scattering signal. I was seeing Rob waving at me. So, okay, so polar region. What happens to this part? Magic hand. So what happens to this part? In a high Q, now I can look at portion of me, or portion of the structure. So polar region basically look at the decay, sorry, it should spell slope, not slot, slope for the scattering intensity at high Q. This means you should look at Q at much, much bigger than 1 divided by Rg. So this is roughly Q equal to Rg equals to 1. So it needs to be bigger, which means you're looking at a fraction of your molecule. So polar region basically says it can understanding a concept called fractal number. How my mass or size scale changes with the ruler or the length scale we're looking at. So if I have a pen, let's look at the pen. So if I look at this pen, it has a few interesting property if we scale with the lens. If we start looking at tiny detail, let's say a few millimeter to 2 millimeter to 3 millimeter, we slowly increase the measurement length. If we put the origin of our observation in the center of the pen, when we first scale the increase the observation size scale, the volume, what we are observing is the mass or a spherical structure, and what you observe is increasing with observation size scale of cubic, right? Until you hit the radius of that, then when we start to increase, imagine there is a spherical structure is keep expanding. After it's hit the radius, then we'll start to see a second scaling of your structure with this material, because now every mass scale with the length, it doesn't increase in the diameter direction. Okay? Is it too abstract, or everybody following this? So in other words, intensity versus Q going to scale at two different length scale. At low Q, when we drop the Q, it's going to scale linearly with the Q vector, because just it's a 1D object versus 2D. If it's 2D, you're going to see two-dimensional dependence of Q by the power of 2. So this slope is basically tell you what's the fractal number and how your structure depends on your intensity. Okay? So a few examples. Polaroid region for 1D object. So if we increase the red circle, your scattering volume increased linearly, right? If I double this, it measures double the radius, but your mass only increased linearly because it's a 1D object. 2D object, when we double the size, my mass doubles twice. In three-dimensional object we already show. So you can look at how intensity scale with Q to understanding a bit about your shape of your object, or in a lot of sense, if you have a polymer that is porous or just a polymer coil, you can look at how does the mass fractal if it's not a solid piece of the sample. So what the mass fractal basically means, when you increase size, how much mass you have changed with respect to your radius. Okay? It is more quiet than I explain the polar region. So any confusion when I explain to Canadian region? So any question for polar region? The application space for this is we want to measure the surface roughness, or mostly in polymer, it's going to look at the fractal number or the dense, or how much voids or how your polymer particles scale with the size. Okay, that's the most common application space for polar region. But if you're doing nanoparticle research, this is very useful. You can look at indirectly to look at the shape and size. I'm gonna use the last 5 to 10 minutes to explain a polymer coil. It's again quite intense equation. I will, please.
Before we get into this, I just had a question. So when you're talking about these size scale regimes, if you're looking at porous materials instead of nanoparticles,
Yes.
how would you determine whether you're in the dilute regime or
Same.
concentrated regime?
I think the same. If you specifically mentioning the filler, such as it's a porous nanoparticle versus solid phase, the same. The different region, polar agonia is just defined by Q. That's the Q value, 2 pi divided by Q with respect to the size scale of your particle. Okay? It doesn't change the fraction only matters in the high Q region, a solid piece of the, let's say 100 nanometer porous particle will scale different with non-porous particle. At low Q, as I mentioned, our ruler is bigger. And I think I didn't explain that one. The ruler bigger, and that also comes a consequence that your measurement resolution also goes down at high Q. So in using a good example, you mentioned a porous nanoparticle in polystyrene versus a gold nanoparticle, which is solid in the polymetrics, assuming they both are 100 nanometer. In the high Q, think about, again, I mentioned ruler is, you can magnify and see the detail. You will tell the difference between gold nanoparticle. But at low Q, porous particle, actually, you can think about a filter in your film, mosaic filter. You just filter out. Everything gets fuzzy because you don't have the power to resolve everything inside. Porous particle actually has no difference with a solid piece of particle with averaged scalar length density for your porous material, right? Think about air effectively lowers electron density for your porous material. So if your porosity is 50%, in the low Q region, what the X-ray see is, again, a solid piece of particle. It didn't see any pore because it didn't have the ability to resolve it. What it see is your solid piece particle just behave like something with 50% electron density. But in the high Q, then you start to further magnify it. You see, oh, you actually has pore, but the other didn't have. So resolution is important.
So you only see a difference in the contrast between the two particles.
No.
So if you were scattering in the low Q regime for a gold particle versus a polymer,
Yes.
the actual intensities would be very different, but the behavior would be very similar as far as
Exactly the same.
intensity dependent on Q.
Yes.
Okay.
Yes. Good call. So now come back to the polymer chain. It's not that complicated. Don't worry about all these equations. You guys all finished the polymer physics 710. But I assume many of you need to review it one more time. So let me quickly explain. Anyone recall this particular function? So this is a probability of finding an end-to-end distance Rij within a polymer core. So this basically says the probability will decay scale with the distance, and this distance is going to be Rij, and this is average distance. So it basically says the probability of distribution will be highest at the Rg, and it will decay with a longer distance. But it's just a general equation, okay? There's one reason we want to keep that equation is basically look at the scattering vector, the form factor. The common thing is shared is Rij, so in the Gaussian coil and in the scattering form factor for the polymer, and this is just a generalized exp, exponent of minus iq. Q is scattering vector, Rij is any given point within your polymer. So this is a general equation. So now we just need to figure out a way how to transfer this particular general equation using the polymer physics knowledge we know. So now go from there. Not too bad. All you need to do is to convert this particular portion to radius of gyration, because this particular part is relevant to radius gyration. If we do that, we can reach it down to this particular equation, which basically says we can pull out all the self term again. I know that some of you are still remember that in the free joint chain. And we can summarize all the cross terms there. So this will be the final equation for any polymer Gaussian coil. 2 divided by Q cubic, Rg power of force, not the cubic. So exponent minus scalar vector Rg squared minus 1 and plus Q Rg squared. It's a little bit complicated, right? But as you can see, when Rg and Q goes up, your form factor will closer to be 0. So let me show you an example. What is the form factor for polymer? And people give it a cool name. It's called the Debye function for that specific function for this. This shows you how your form factor would be dependent on scalar vector Q and Rg. So intensity is basically square of this. So you can, if you look at that, what it plot is a polymer with a radius of gyration about 100 nanometer, 100 angstrom, 500, and 1,000 angstrom. Generally, you see a shift to the left. That's very common because, as we explained, scattering is inverse space. The bigger the feature, everything will skew to the low Q. But if you look at the red curve, you see the Ganier region at the very low Q, which is a little bit hard for me to reach. Tiny bit here, okay? That's a Ganier region. When your Q is low enough to see the whole polymer coil, you will see intensity is plateau. Okay? Ganier region is signified by almost a flat Q, flat intensity versus Q. Okay, once we pass Ganier region, we reaches in the middle one and the polar regions in the end. It's very different with nanoparticle. The polymer don't have any clear minima you can use to measure the radius gyration. Right? So if you recall what we talked about spherical particles, you can use where the minimal Q is, use that to get to what the value of your Rg, or you. So in this case, we have to use the Ganier region to probe the Rg. In other words, you need to plot log intensity versus Q squared to get what the Rg value. Okay. So I think we have quite some information. In the next class, I'm going to introduce a very powerful software. So SASView is basically a software the community developed to analyze small angle scattering. It's very powerful. It can analyze the data to do all kind of fitting, or it can do modeling. What I mean modeling is you tell what the shape you have, what the structure you have. It can plot the expected scattering curve for that. The link I already posted in the Canvas, so go ahead and take a look at this software in general. Read a little bit about their introduction parts. I'll do a quick demo, probably 5-10 minutes, because we probably don't have time to go too deep into that. But this is everybody's go-to tool when you analyze the small angle scattering. When you want to get the form factor, when you want to know what the dimension of your any particle. We can do forward or backward calculation. Forward means I tell it any arbitrary shape, it will give me a scattering curve, theoretical scattering curve, okay? You can tell I have a bottle, what the scattering would look like, or if I have shape of me or my watch, what it will look like. It can do anything, as long as you tell what the shape, what's the dimension, because it's all governed by that Fourier transform equation for form factor. As long as you know electron density and shape of it, you can get the scattering. So backwards calculation is more powerful because that's more useful. A lot of times you don't know the size of shape of your structure. You actually wanted to measure it. So that's where this software comes into powerful is you tell it what the scattering data look like, I versus Q. That's just you measure in the detector. And you tell a little bit the parameters that you know about your structure. Let's say, I know my polymer maybe look like a rod-like material. And my structure might have a dimension of, smaller than 100 nanometers, or I might be a cylinder structure. So you can ask a software to, hey, give me the findings of what is most likely size, length would give rise to my scattering profile. We call it modeling of the data. So you do inverse calculation of probability check from your scattering data to your real structure. Okay, that's actually 99% of the time people use it. Seldomly people do forward calculation because you already know your structure. You probably don't need no scattering curve. But a lot of time we know the scattering curve. We want to fit out the data. So here comes a challenge. You have to let the software know a little bit about you. Because the same scattering curve might be coming from several shapes. So in other words, sometimes it's not a singularity answer. So a couple of structure, if they're similar, they might give you very close scattering curve. So the bad calculation, if you don't give some boundary conditions, it could be really give you some weird answer. Okay? So with that, I want to wrap up today's lecture. Any question for me for this part? We talk about Gneiss region. We talk about also polar region, and lastly we covered a little bit about the form factor, the Debye function for any polymer chain. If not, there's one more thing I want to finish is the quiz. So when we talk about 3 parameters we need to worry about when we perform an X-ray. We talk about absorption. I think we mentioned it a lot. So make sure before you do measurement, do a quick out-of-envelope calculation about absorption. Second is contrast. Make sure you do a scattering length density calculation, understand if there is net contrast. Last but not least is the size scale. Make sure you this feature you're trying to measure matches the geometry of your setup so that you can measure it. Okay? With that, let's wrap up. So in the next lecture, we're actually going to go into consider slightly more complex case. Up to now, we only consider dilute. Next lecture, we're going to start to put in something called structure factor. Up to now, everything is form factor. How mic looks like, or we never talked about our interaction, but it's very important, right? As human beings, as nanoparticles, or anything, how you interact with your surroundings is important. We're going to start talk about disorder system. Talk about liquids. In that case, you can imagine it just randomly order the particles with a given distance. So you should read a little bit end of your chapter 2. There's a little section about that. Then you should start reading the chapter 3 on disorder liquids. Okay? With that, let's finish today's part.